All right, our next guest speaker is Ralph Cohen. He's a mechanical engineer. He's designed semiconductor factory clean rooms for over 30 years. Started and tested industrial air pollution control equipment. Has Peace Corps Liberia design and construction, taught fluids and hydraulics at OIT. In the most recent 10 years, he's been an independent engineering consultant to the industry. Thank you, Ralph.
Thank you. So how many of you have taken something apart just to see what was inside? Great. And how many of you know someone who's an engineer? How many of you have talked to the engineer about what they do? How many of you understood what they told you? Right. Well, I wouldn't expect you to totally understand. It's kind of a foreign language in a way. So that's good. It sounds like quite a few of you. And, how many of you already know you want to be engineers? Okay. All right. Put this away. So I'm not here to convince you that you should be an engineer. I wouldn't try to do that. Didn't work on my daughter. But I just want to tell you why engineering was a good career for me. So I'll give you a little of my background. When I was 10 to 13 years old, I was raised on a poultry farm, a chicken farm in New Jersey, and I collected and packed eggs as chores. I got to drive the tractor, repaired lawnmowers and bicycles. I took apart things, just as some of you have, to see what was inside. I generally wasn't able to repair things at that age. I built simple one-transistor radios. Back then, you didn't have the complex devices that you have today. So one transistor, one or two tubes, that was about it. What you heard was not very pleasant. You had earphones, nothing like the technology of today. I helped build a go-kart, one of these four-wheel things with an engine that we'd race around the farm on in spare time. I used to build gasoline-powered airplanes out of balsa wood and paper and flew those. I did science fair projects. I read books and magazines about science and mechanics. Mostly magazines. I wasn't really particularly into literature at that stage. So what I learned on the farm, I call these farm systems. So you take a number of things, such as an electric motor, plus something called an auger, which is kind of like a large drill bit that you might drill a hole with, but if you rotate that, you can actually use it to move solid material or like chicken feed. So I learned about those. Electric motor plus a gearbox, which is something that slows down the speed of the motor and it increases the power, and a thing called a drag chain you could use to move feed through the chicken coops. We had about 10,000 chickens, and we didn't really want to feed them all by hand, so we had these automatic feeders. They would break down, and at some point I was able to work on those and help repair them. Also had a heater, electric heater, plus a motor and an air compressor. And this is a kind of a washing machine. All eggs are typically washed. If you don't wash the eggs, they're kind of gross to look at. So we'd wash the eggs, and a motor with a fan blade. You could help cool the chickens. It was very hot and humid in New Jersey in the summer. Take an engine and attach it to something called an alternator. It makes electricity. Sometimes when we had bad snowstorms, power would go off, and the chickens need electricity. We needed to function on the farm, so we had our own fairly large generator. And then lastly, you take a motor and add it to a pump, and you pump water out of a well. We didn't have city water. We had a 75-foot deep well. So I was able to learn quite a bit about systems. So a couple of years later, I guess I was in high school and trying to think about what I want to do in my life, and adults would tell me, you'd be a good engineer. And I'd say, what's an engineer? And so I did some research. So what do engineers do? Engineers change the world all the time. It's kind of a kind of a large-ish statement. We dream up creative and practical solutions to problems. We work with other smart and inspiring people, and sometimes we invent, but we usually design and create things that matter, or at least they matter to somebody. So, but would I enjoy it? That was the question. Qualities most engineers have. First, they're typically curious. They like to know how things work. They like to know how the world works. They enjoy the creative process. And creative is, you can be an artist and be creative. You can be an engineer and be creative. You often have to come up with something original. I think you typically would have a strong interest in science and math. You want to make the world a better place. You enjoy a good challenge. Not necessarily an impossible challenge, but something that you feel you can solve and feel good about it. And then it helps to have a big picture understanding. You kind of see a large canvas of a project, but you also know that you're probably only one of us, one in a large team solving that, and you understand your role and you understand everyone else's. So I ended up in engineering school, engineering science school, small school in New Jersey called Stevens, and I found the first year was mostly theory, and I'd have to say it was really tough. I was a pretty good high school student, but I guess one of my greatest fears was I was going to flunk out. And so I studied as hard as I could, thinking as long as I did my best, if I wasn't successful, I gave it my best. Well, I did okay. And during the 4 years, I came to enjoy the understanding about how science is applied to the material world. For example, how one form of energy is converted into another form. So like you burn a fuel and you get steam, or you get electricity. How elements are combined, so how you combine iron and manganese and chrome, and you end up with stainless steel or steel or polyethylene or PVC, different plastics. So that's a study of materials. And then how machines are designed. I did study some machine design, although I never really did much in that. But those are just some of the things that you study as a mechanical engineer or can study. So I had some useful jobs as an engineer, or becoming an engineer. The first one was a summer job. I cut paper in a paper factory. Doesn't sound that exciting. It probably wasn't that great a job, but it paid, helped me get through school. But I did get the opportunity to look at machines, how you go about controlling, moving large piles of paper, cutting them to a 64th of an inch. These were packaged into drafting paper, which was used before CAD. We have CAD now, so a lot of drafting paper is obsolete. I worked in car and motorcycle shops. I'll talk a little bit more about what I learned in motorcycle shops in a minute. I inspected magnetic tape, kind of like the tape you have in the cassettes, but this was used in early computers. It had to be very high quality so you didn't record defects. And then I swept floors on a New York City skyscraper, 42 stories. Again, what would you learn sweeping floors? Well, one of the cool things about building under construction is you get to see this bare skeleton of the building. There's no covering on the walls. There's no ceiling. So if you're interested in engineering, you kind of look at how the things go together, how steel's connected, how the ductwork and the pipes and the wiring are all put together into this network. Everything kind of. I mean, you have the same thing in a school. Any building has a lot of systems you don't see. They're all covered up already. But I learned quite a lot that way. The motorcycle systems. There's at least 4 systems in a motorcycle, and so the ignition system, something that provides spark to ignite the fuel. Electrical system, you have to charge the battery, you have to start the motorcycle. There's lighting, there's switches for brakes and accessories. There's a fuel injection system, so something has to control how much fuel goes into the cylinders, and it's done with computers today, same as in your car. And then there's hydraulic braking today. and anti-skid control. They're really quite complicated, and kind of the cool thing as a engineering student, I guess I was a junior at that point, I was starting to get courses in some of these things, and here I was working hands-on, and it turned out I knew more about electrical than any of the mechanics, so they gave me all the electrical troubleshooting problems, and actually what I learned in college was very applicable. And since graduating, it was mentioned a little bit in the introduction, I first fixed and tested air pollution control equipment. These were devices that take the particles, the dust particles out of the air. If we didn't have these, our air would be a lot more polluted. I did that for a couple of years on power plants and paper mills and steel mills all over the U.S. Then I kind of realized that I might have a boring life if I didn't do something a little more exciting than work on these type systems. So I applied to the Peace Corps, and I was sent to West Africa, country of Liberia, and I designed and built schools and roads there for a couple of years. When I came back, I started working in design of electronic chip factories. Started with Texas Instruments, and later with Intel, and in between I had one short duration project where I was involved in designing a TV picture tube factory in China. That was before most of you were born, I guess, back in the 1980s. And then lately, last 12 years, I have my own consulting engineering business. This is what a precipitator looks like. It's there's a power supply, 40,000 volts, which is rather high. Definitely electrocute you if you touch it in the wrong place. And there's where the red arrow, the orange arrows are, the air goes through, and the electricity puts a charge, kind of like static electricity. If you notice on your comb, if you see any dandruff, we don't like to see that, but if you do, it's the static electricity is attracted to the comb. The precipitator works on the same principle. The high voltage charges the particles. They are attracted to the metal plates inside, and then we can knock them off and collect them and not have it go up into the atmosphere where it causes asthma and other problems. Semiconductor clean rooms have a lot of systems. There's fresh air and exhaust air, so we have to bring outside air in because we're trying to protect workers. With exhaust systems, we turn the air over and we filter it so that there's no particles inside. We have to purify water that's used to rinse the chips, and there's various gases. We know that the air we're breathing right now has a lot of nitrogen in it, but also has oxygen and argon and hydrogen in it, and we extract those from the air and use them in the process. There's waste collection and treatment systems. There's chemical and gas distribution. There's cooling and heating and compressed air. And there's electrical power distribution. There's control. So they're really complex, and it takes a lot of engineers to design them before the people actually even show up to start making chips. So here's just a few pictures of me. On the upper left was when I was in the Peace Corps. I was a little bit younger then. The upper center is the team building the school. The upper right is a pile of bicycles at a train station in Europe. The lower right, I was suffering a little jet lag, and I was studying welding in Japan. In the center lower, we were enjoying a meal in a Japanese restaurant, and then lower left is an aerial view of Ron Leraker's Hillsboro semiconductor factories, some of them that I worked on. So what's the fun part of engineering? It's you get to be creative and solve problems. It's never boring. You often get to travel worldwide. In some cases, you get to live overseas. I was able to live in Ireland and in Africa. You get to go out in the field and work. You're not necessarily constrained to an office. Sometimes you work in a laboratory or go out to the construction site or go on the shop floor or making something that you may have designed, you get to see tangible results. Some types of work, you labor for years and you never really see the results of your labor. With engineering, you typically design something, it gets built, it's made to operate or function. You can stand back and say, I worked on it, it worked, it didn't work, what do I need to do better next time, but it's tangible. And that was important to me. It's a flexible job. The salaries are usually pretty good. You get to make a difference, you get to change the world. And sometimes you get to invent something. So this was a project I worked on over the last 3 years, inventing something. And actually found out yesterday in the mail that actually we did get our patent. So why was it a good fit? I loved solving technical problems. From a very young age, I enjoyed science and applying it. I liked the wide project variety I had. I enjoyed working with people, often smart people, smarter than myself, and I look forward to going to work. The time flew by. I think that's important. If you're working, you're going to spend a lot of your life in working. You should be doing something that you enjoy. So you don't want to be watching the clock. You want to get in the morning really charged up and say, oh my God, it's 5 o'clock or 6 o'clock. I guess I have to go home. And then I felt what I was doing had. So that's it. Any questions?
Who's got a question?
Yes.
What was your invention?
It's something that relates to welding stainless tubing. So when you're welding stainless, the weld site has to be isolated from oxygen. Otherwise, it becomes oxidized, which is to say it becomes black, and that causes impurities. So you're not allowed to have impurities if you're using the system in something, say, conveying ultra-high purity gas in the semiconductor factory. So this particular invention reduces the amount of time it takes before you make your weld by 90%, and it also reduces the amount of argon, which is an expensive gas, by 90%. So whereas it might typically take a half hour, 45 minutes, up to maybe several hours to get ready to make the weld, with this invention you could make your weld within about 5 minutes or less.
How long did it take you to find out how to make that invention?
Well, I'd say we probably the initial idea came fairly quickly, but as we went through the process, there were more complications. So each stage of the way, we were challenged. So I'd say generally, and we weren't doing it full time. This was not a full-time project for the three of us, because the people I was working with had full-time jobs as well. But in general, I'd say it took about 2 years from the time we sat down till the time we finished the testing, and we went through about 3 prototypes as well. And they probably spent at least $100,000 all along the way, so it took a little bit of capital. And I don't expect to get rich on it, but I just wanted to do it. Hard to believe for me.
What does your consultancy firm do?
Right, so I'm a one-person consulting firm. I deal with mechanical engineering problems, and I've done a fairly wide range. I've done studies for a consortium that manufactures semiconductors, which is a pretty vague description, but why don't I just say more recently, in the last couple of years, I've done about maybe 4 projects where I go into a semiconductor factory like Intel, and I look at how their mechanical systems are working, and I study them, I collect a year's worth of data, I analyze the data, and then figure out, make recommendations on how they can operate more efficiently. And a lot of it has to do with recovering heat that normally goes into the atmosphere, but we can recover it and use it in the process. Sometimes can save anywhere from $500,000 to maybe $1.5 million in annual energy costs by spending some money to change the configuration of the system.
Yeah, thank you.
So we met at Engineers Week when you were there manning the booth for the Society of Professional Engineers. Could you tell them what that is?
Yeah, so the Society of Professional Engineers is a national organization. They look after the interests of engineers in general, and they oversee the licensing process. Is probably one of the important things. So if you want to become a professional engineer, which is what I am, and that entitles you to practice engineering as an individual, and it's required in most states, and it's required if, say, I want to design a bridge or a high-rise building, I must be licensed, which means I have to pass certain tests and have certain education. So they administer the testing, which first test you take when you graduate college. That's the earliest you can take it. It proves that if you pass it, it proves that you did your homework in college. And then 4 years later, after you have experience, you take a second test, which is an 8-hour test, which tests whether you have learned something in those 4 years and are now competent to practice on your own without someone else checking your work. So, and we have monthly meetings. I bring in speakers who talk to us on a wide range of topics of interest to members to try to keep them sort of up to speed with what's going on. Someone from Hanford Nuclear came down and talked about the cleanup. Someone from the Port of Portland talked about the Willamette River pollution and what that cleanup's going to look like and things like that.
All right, thank you very much. That's it.